Okay, let's get some practice working some Chapter 38 problems. If we had a laser to do some eye surgery and its wavelength is 652 nanometers with a 20 millisecond pulse duration, and we know the average power during each pulse is 0.6 watts, let's calculate some energies of the laser and of each photon and figure out how many photons have to be in each pulse. So we know that the power is going to be equal to the energy divided by time, right? Joule per second is a watt. And so for part A, the energy is going to be equal to the power multiplied by the time, or 0.6 watts multiplied by 20 milliseconds, 20 times 10 to the minus 3. And so the energy is going to be equal to 1.2 times 10 to the minus 2 joules. If we want this in electron volts, we need to say that in 1 electron volt we're going to have 1.6 times 10 to the negative 19th joules, and we can cancel the joule out, and it's going to work itself out to be equal to 7.5 times 10 to the 16 electron volts. Now let's go ahead and figure out the energy that one photon has, and what we're going to do is we're going to say E is equal to h times f, or hc divided by lambda, since I've been given lambda. And I want to kind of mention something about Planck's constant. We said Planck's constant was equal to 6.626 times 10 to the minus 34th, and it had a unit of a joule multiplied by a second. Sometimes we will see it in electron volt seconds, and we can say that h is going to be equal to 4.136 times 10 to the minus 15 electron volts multiplied by a second. And that's kind of convenient if we just want to always work in electron volts. So you probably want to have both of those guys written down. And I'm just going to go ahead and work this guy in electron volts just for practice. So 4.136 times 10 to the minus 15th multiplied by the speed of light, 3 times 10 to the 8th, divided by the wavelength, 652 times 10 to the minus 9th. And we're going to get the energy for one photon to be equal to 1.91 eV, and I'll let you convert that to joules for practice. Now for part C, let's figure out how many photons are in each pulse, and we know that if we know the energy in the laser and we know the energy per photon, then all we have to do is divide those two guys out, and so we're going to say 7.5 times 10 to the 16th eV divided by 1.91 times, or 1.91 eV per photon, and we're going to just simply divide those guys out and figure out they're going to be 3.93 times 10 to the 16th photons, so a whole lot of photons. So let's go ahead and figure out the minimum work function that's required for metal to have if visible light is able to eject electrons. And a couple of things to kind of keep in mind for this guy is we know that the 380 nanometers has a lot of energy. We're starting to approach UV, and so we're actually going to be interested in this guy because it has far less energy. So maximum wavelength and minimum, or the highest wavelength or the minimum frequency. And essentially we're going to be taking a look at this guy right over there. EV naught is equal to h times f minus the work function. And in this case right over there, we could also say this is going to be equal to hc over lambda minus the work function. And if we're just barely able to eject photoelectrons, then this guy right over there is going to go to 0 because we're not going to have a work function. And so we're just going to say hc over lambda is going to be equal to the work function. So that's got to be equal to, I'm going to use the electron volts version of Planck's constant again, 4.136 times 10 to the minus 15th, and again that is electron volts multiplied by seconds, multiplied by the speed of light, 3 times 10 to the 8th meters per second, divided by 750 times 10 to the minus 9th, and I'm going to get 1.65 eV. On problem number 17, we're going to have an X-ray that is going to collide with a stationary electron and it's going to come off with some new wavelength. So got my original wavelength and got my new wavelength. And what we're going to do, there we go, make that a little bit prettier. What we're going to do is we could actually figure out the angle that this guy is going off at, but the problem doesn't ask for that, it actually asks for the energy. So kind of how do we do this? Well, we're going to say the energy before the collision occurred has got to be equal to the energy afterwards. And so here we're going to have hc over lambda is equal to hc over this new wavelength plus whatever kinetic energy that this that the electron gained. And so this is kind of what we're interested in. And so we're going to say 4.136 times 10 to the minus 15th, that's in electron volts, multiplied by 3 times 10 to the 8th, divided by the 0.1 times 10 to the minus 9th meters, is going to be equal to 4.136 times 10 to the minus 15th, again, electron volt seconds, 3 times 10 to the 8th divided by 0.11 times 10 to the negative 9th. And by the way, we are very happy that the wavelength has gotten longer because the energy has left the photon, plus the kinetic energy that is gained. And we're going to get 1.13 times 10 to the 3rd electron volts is going to be the kinetic energy when you go ahead and you solve that guy. Okay, and now a problem with a laser pointer. The laser pointer has some wavelength, and it's actually an ultra-short pulse. And what does Heisenberg's uncertainty principle limit the pulse duration to if we have uncertainty in the energy to be 1%? So the first thing we need to do is figure out how much energy these guys have. So we're going to say E is equal to hc divided by lambda, or 6.626 times 10 to the minus 34th, multiplied by the speed of light, 3 times 10 to the 8th, divided by the wavelength, 625 nanometers. And that tells us that the energy that we're talking about is going to be 3.178 times 10 to the negative 19th joules. And I know 1% of that is going to give me my uncertainty in my energy to be 3.718 times 10 to the minus 21, right? Just multiply it by 0.01. And actually I'm looking for the minimum duration, and I do know that delta T, delta E has to be greater than or equal to h bar over 2. Since I'm looking for the minimum, I'm going to set it equal to. And so delta T is going to be h bar over 2 delta E, where this is going to be 6.626 times 10 to the negative 34th, and there's my 2 pi, so there's h bar, multiplied by 2, multiplied by 3.718 times 10 to the minus 21 joules, and you type all that in, and you're going to get a really small number, 1.6 times 10, or 1.67 times 10 to the negative 16 seconds, which is actually going to be 0.167 femtoseconds. And last but not least, a little bit of Compton scattering. So we're going to have a photon that is incident upon an electron, and then it's going to scatter off of it, and it's going to be moving in the backwards direction. Right, that's this guy right over here, and that actually is going to tell us that phi is equal to 180 degrees. And what we're going to do is and the electron is going to be moving off like that. What we're going to do is we're going to say the momentum beforehand has got to be equal to the momentum after, and we know that momentum is going to be h over lambda for a photon, so we're going to have h over lambda is equal to h over lambda prime, because this guy right there imparted some of its energy and momentum to it, and so it changed its wavelength. It should be a little bit longer, plus the momentum of the electron, and this is what we're looking for. So we know the wavelength, we just need to figure out what the new wavelength is, and so we're going to take a look at what we know for Compton scattering, that the change in wavelength is going to be equal to h over the mass, and I forgot to mention this is actually the mass of the electron that it scatters off of, multiplied by the speed of light, and then 1 minus cosine of phi, where this is backscattering, so phi is equal to 180 degrees. So all we're really doing is we're going to say, okay, well, I know that this guy right here is going to evaluate to -1, so I'm going to have 1 minus -1, and this is going to evaluate to 2, and so the wavelength is going to be the original wavelength plus 2h over mass multiplied by c, which is going to be 0.09. I'm just going to leave that guy in nanometers, plus, actually I'm going to move down here, so that's going to be 0.09, I'll put it into meters, times 10 to the -9th, plus 2 times 6.626 times 10 to the -34th, divided by the mass of the electron, 9.11 times 10 to the -31, multiplied by 3 times 10 to the 8th, and I'm going to get my new wavelength to be equal to 0.09485 times 10 to the -9th meters. And so now what I'm going to do is I'm going to say that the momentum of the electron is going to be h over lambda minus h over this new lambda. And you're going to go ahead and you're going to type all that in. I'm going to spare you from watching that. It's going to be 1.43 times 10 to the -23rd with a unit of kilogram meter per second.